You shut down the customers, right? You do the rolling blackouts. They call it nicely rolling blackouts, not the entire blackouts. Right? It happened the same way in February, on February the 1st in here, in College Station. I was having lunch with Anton, right? And we got the blackout in University Drive. Right? And that's not the only problem, actually. If you ask the CEO of ERCOT is again, a great manager from Texas. What's the #1 thing that keeps you awake at night, right? Is they have these commercials always saying what keeps you awake at night. The thing keep him awake at night is the wind ramping. So what is wind ramping? The wind ramping is exactly as what we described. The sudden drop or sudden increase of a significant amount of wind power in a very short period of time. Right? Why? Because this kind of a sudden increase or sudden drop cannot be followed by the other means of supplies. Demand, we are used to this philosophy of turning on and off the lights whenever we want. We don't care what's going on in other places, right? So we basically have a fixed demand, and on the supply side, you have a bunch of slower units, which simply cannot catch up with this sudden drop or sudden increase of wind, right? So what do? Well, exactly as you said, let's put a lot of natural gas power plants. Then, how expensive are those natural gas power plants? Must be pretty expensive, right? Nowadays it's a little bit better, but in the long run, think about the price volatility there, right? And when you're driving the car, when you are in a congested downtown area, you tend to speed up and down your pedal like this. Think about the emission because of that. Think about the fuel economy because of that. So if you're running a natural gas power plant like that, think about the fuel economy, think about the associated environmental cost for you from the environmental side, right? So the perceived environmental and economic benefits of the quote renewable energy may be largely offset by the way how we operate the grid, by the very nature of the electricity system, right? So you have to take a very careful view and very systematic view of the overall picture, rather than just say, let's push for more wind turbines, let's push for more solar panels. Right? So in a nutshell, this conveys the message. Now, it is not to say that let's just go back to the old days. I believe that there is a way out, and the way out is how do we start to turn a lot of, we are living in a world of very, very, very many smart people, right? People have really kind of contributed to many, many different aspects of this problem. You talk to a statistician, the wind power forecast today is much better than the wind power forecast 30 years ago, right? If you talk to the Vestas people just now, the wind power controller is, it's way better than before. It used to be these, squirrel cage induction motors. Now they're doing these power electronics assisted doubly fed induction generators, which is very, very grid friendly, if you wish. So I think the key question is really, how do you start to build from this, I call component level innovations, right? And how do you somehow translate that into some kind of a quantifiable system-wide benefit? Be it a lower cost for everybody, or be it a less blackout for everybody. These are the kind of things that we are trying to work on. That is, we don't want to say we are the best forecast or we are the best control of the wind turbine. Rather, we're trying to say, having all these components in place, how do I translate that into your monthly bill that is lower than last year's? And still, you have more wind and solar penetration. That's what we are doing. And I think for this group, it is really an exciting engineering field with this great social impact. Well, I had a discussion with Omar before. I asked him, are you money-driven or purpose-driven? Right? It's a very philosophical question. He told me he was not money-driven. He told me he is purpose-driven. And I believe many of you are the same. I think this is really, I think, a field where not only you can have the fun of enjoying the intellectual discoveries, but also you can have the great social impact. I don't know if Taylor has bragged you about that, but your activities here has already attracted the attention of the top level government officials in this country. The Deputy Secretary of Department of Energy in the US actually was here on Monday with the Energy Club. Can you believe that? So that's what I'm saying. What you're doing, you can have great social impact as well. And I think this social impact can only happen if we have solid fundamentals, engineering fundamentals, if we have very solid engineering fundamentals. And we couple that with domain expertise. You know, you have to know something about electricity grid, or you have to know something about, I don't know, oil plants or natural gas plants. And you have to really kind of go beyond your comfort zone and then start to think about these broader issues, cross-boundary thinking. Right? You have to know, what are the good things that computer scientists are working on that I can leverage. Right? I have a student now working on a problem, which we hope we can report to you in a month, about using Facebook and Twitter to reduce average home consumption. You have to know something about telecommunication, because in the future it's going to be highly sensed and highly communicated grid. Also, you have to know something for sure about econ, because at the end of the day, you have to drive down the cost. And the driving down the cost is not just by improving, it's important to improve the component level conversion efficiency, right? There are a lot of people working on the materials, right? We found a new solar cell, we found a new turbine material. That's all good, but I think a lot of low-hanging fruits are there in which you can improve the grid delivery efficiency. So if you have seen this energy spaghetti chart, about 30 to 40% of energy is being wasted on the way to your house, right? 30 or 40%, think about that. It's equivalent of how many new coal power plants or how many new natural gas power plants, right? If you were just, improve that part of the efficiency. So I think that is really how we think about these problems. If nothing else, I hope that at least you can take this message away from this lecture. Okay, these are the big words. Now let's talk about some specifics. Well, the specific, let's look at a specific, a particular problem of the scheduling problem. So, how many of you are from electrical side of the engineering? Okay. Okay. The idea of scheduling is the following. You turn on the light and turn off the light. We are doing something here, right? We are doing something here. Because electricity cannot be stored in large amount in near real time. Actually, you know what? Somewhere out there, there was somebody who is actually, playing with a generator to follow your decision here. You don't know about that, but they're doing that. So that's the scheduling problem, right? That is, I want to somehow maintain as an entire grid the supply and demand balance in almost near real time. If you think about it, it's actually quite a complex problem, right? They don't know what you're doing, but they somehow manage to follow you. So that scheduling problem becomes much, much more difficult. The reason is there used to be only one source of uncertainty, and that only source of uncertainty is you and me, that is the consumers, right? Because all the other parts, the supply, coal power plant, nuclear power plant, natural gas power plant, they are all somehow fully controllable, right? You can, whenever they are online, you can always schedule them to desired level of output. Now you are talking about 20% of supply coming from renewables. So the 20% of the supply coming from the renewables, what if the supply suddenly became, not as high as what you desire it to be, right? So the uncertainty will come from not only the demand side, but also from the supply side as well, right? So now the question is, now I have more uncertainty in the system. How should I somehow manage the instantaneous balance of supply and demand, again, in near real time? And another important thing is, you want to somehow minimize the total cost, right? Because a simple solution of maintaining the real-time supply and demand balance is to say, let's just build a lot of natural gas, and they're very fast, and they can follow. But they might be very expensive, right? You still have in Texas, you have about 12% or 15% coming from nuclear, right? Those nuclear power plants is on, and then they're on forever, right? Not on forever, but on for a year, right? They basically serve just constantly. Now you think about, you cannot tweak those power plants big way, and you have limited tweaking for natural gas, and also they're very expensive. You don't want to tweak that much, and then you can tweak the coal, but the coal is very slow, right? But then the wind became very fast, and they're fastly changing. How do you somehow manage all this together, right? And still you want to minimize your cost, because again, you have a higher cost solution, but that is not desirable. Right? So this is basically how you do it. Some of you who are very familiar with that, bear with me. The scheduling problem can be, broadly speaking, classified into two sub-problems. Now let's look at what time is now. That's 5:53, right? 5:53. So at 4 p.m. yesterday, in a place called I think it's Taylor, Texas. Right? That is where ERCOT is. They actually run an optimization problem at 4 p.m. yesterday. They forecast what is going to be the hourly expected demand of electricity for each hour of today. And they try to minimize the total